Yes, my name is Anton. I'm a second-year PhD student from Lund University in Sweden, and I'd like to present our work on property probes today. So this is joint work with my supervisors, Göran Ledin, Niklas Fors, and Adrian Popp. So the paper and this presentation deals a lot with program analysis, and I feel like I need to begin by defining what do I mean, because I use a very wide, slightly incorrect definition here. How we use it in the paper, we say that anything that has code as input and produces some form of usable output can be seen as an analysis tool. So, of course, this includes things like type checking, data flow analysis, and linting. Sorry, let me just fix this. But slightly less conventional interpretations of the word, like code generation, bit printing, syntax highlighting, diffing, that's also included in the scope of what I'm talking about here. So the way the world of analysis tooling is supposed to work is something like this. The user has written an input statement. This is Java, and they're violating the type system. You can tell because there's a bug there. This is fed into the analysis tool, which in this case is a type checker. It performs some internal magic, and as output, we get these red squiggly lines. Now, for those of us who create these tools, usually during implementation, we make a mistake, we take a shortcut, we do something wrong, and whoops, there's a bug inside the tool as well. And now we don't detect the issue anymore. We get a false negative. Could also be the opposite, that the user has done correctly, but we give a false positive. So when this happens, what do we do? Well, we need to look inside the tool and try to figure out where do things go wrong. Problem is that there's many places where it could be wrong. If this analysis tool was a compiler, for example, then there'd be a front end, there'd be some semantic analysis, some optimization or rewrites, and some code generation. They're all sort of glued together. And we need to figure out where is the bug. In addition, perhaps the bug only manifests for this line of code, not in any other location. So wouldn't it be nice if we could take all these sub-analysis steps one by one, just cherry pick one, and then cherry pick a line of code and apply those together and see a sub-analysis result? That would make our job a lot easier. But how do you do that? Well, of course, you use property probes. So the way we define property probes is a live observer of a property on an AST node. So this illustration here is basically the same thing I had 2 slides ago with a code snippet and sub-analysis step. But here, the code snippet is this variable reference x, and the sub-analysis is this type. And we would expect the probe to tell us that the result is int. Breaking this down, trying to put it into context, evaluating a property and showing results. This has some connections to watch expressions you find in many debuggers. Being live is, of course, part of live programming. And then we do things on top of the AST. And you take these different things, merge them, and somewhere in the middle, you'll find probes. But the best way to demonstrate this is with a demo. So we built a tool supporting property probes, which we very cleverly called Code Prober. And here it is. So it's a little small. It's a web-based tool. It's mainly a text editor. This is the Monaco text editor, and I can interact with it. I can write, edit. But the interesting part and the important part is this. This window right here is my property probe. So a probe has 2 parts. The top part is input, and the bottom part is output. The top part tells us that the probe is looking at a variable declarator node. The property name is final, and here is the position of the node we're looking at. And if I hover over that position, the corresponding range in source code gets highlighted. And then in the output, we see false, because this declaration is not final. But I can make it final, and it flips over to true. Now, this is probably the easiest possible sub-analysis I can show, so let's make it a little more interesting. I want to look at constant propagation for this multiplication expression here. So to create the probe here, I just right-click anywhere within the multiplication, select Create Probe. Now I get the list of all the AST nodes that overlap with the place where I clicked. And if I hover over the items in the list, you see the corresponding range in source code gets highlighted. So closest to where I clicked is a multiplication expression, and that's what I'm interested in. So I'm going to click it. Now I get a new list containing all the properties that are available for me to play around with. So in introduction, I broke down an analysis tool as these colored boxes that are glued together. Well, the items in this list are the colored boxes you can think of. So it's quite a lot, but I know the name of it that I'm after. It's called constant. And here we go. So 1, 2, 3 times 2 is 2, 4, 6. This seems right. And again, I can make changes, and I get very quick feedback. Eventually, it overflows as well. All right, let's look at a different scenario. I should also mention, CodeProber doesn't do any analysis itself. It just lets you look inside of another analysis tool. So the set of functionality that's available depends on what tool you're using together with CodeProber. In this case, it's a Java compiler, but if you use it with a Python interpreter, then there would be completely different functionality available. So let's say I do something like this. And now I want to simulate what happens when I make a change to my tool. So in this case, this is pretty printing my code, and it removes some empty new lines. This all seems fine. But let's say I want to make a change. I want that empty blocks are printed like this. So open and close the curly brace on a single line. So what I do, I go into my editor. I happen to be in the file that does pretty printing for blocks. I add a special case saying if the block is empty, just print open and closing curly brace. And now I start a recompile. And I'm not touching my computer right now. It should finish the rebuild in roughly 4 seconds. And look at the probe in the background. So whenever CodeProber doesn't just monitor the state in the browser here, it also monitors your tool. So whenever you rebuild it, all probes get refreshed. So one way you can use this tool is just open a few probes, all the information you're interested in extracting. Then you move CodeProber to a separate screen, and you keep working away on your code. And whenever you recompile, you can glance over on your secondary screen, and fresh values are available. All right, let's go to a little more flashy. So probes can also output things that don't appear inside their own body, but also inside the text area. So in this case, the probe is displaying a control flow graph. And I can do something like this. And you see, as I'm typing, whenever I reach a valid syntactic state, it reevaluates. So yeah, if you're working with control flow graph construction, you can inspect that as well. Perhaps not very applicable to a lot of people, but it's fun to look at, so that's why I usually show it. Finally, I'm going to show my favorite attribute, which is bytecodes. So I'm using this with a Java compiler, and that means that I can just ask the compiler, hey, if you were to compile this method right now, what bytecode instructions would you generate? And again, you get this very quick feedback, and you can play around and see how it generates. So again, if you're working with code generation or working with optimization, this could be a very nice in and out, what do you call it, playground to just see that things work as they should. But even if there isn't a problem, this is just a nice way to play around and build an understanding of how the Java class file format works. I knew very little about the format before I started using this attribute, but now, through just playing around, I know about a lot more. So CodeProber is not only for finding issues, it's also for just exploring, building understanding. So that's why in the paper we describe it as an exploration tool, not a debugging tool necessarily. All right, I think that was everything I should show. All right, so that was the demo. We looked at a very simple probe, looking at whether a declaration is final or not. We went up slightly in complexity, did constant propagation, then all the way to rendering a control flow graph and bytecode generation. And like I said, all the functionality that's available depends on which tool you're using it with, but you can usually do quite a wide range of things. So just briefly about the architecture. CodeProber is implemented in a client-server model. The client is written in TypeScript, uses Monaco for its editor. It communicates with the server written in Java over WebSockets, and it tries to do as much as possible while staying language agnostic. Any text-based language is supported here. And to sort of make it concrete at which language you're working with, you need to plug in your analysis tool. In a demo, this was a Java compiler, but again, you can plug in anything. And except it has to run on the JVM. That's one hard restriction right now with how we implemented it. So I went out, I took a few existing tools, I tried to adapt them to run in CodeProber. So we have Wala, PMD, and Spotbugs, and they all work to some degree. We also have a bunch of tools that we built in our department. So ChocoPy and Featherweight Java are subsets of Python and Java, respectively. We have Simply C, which is a very simple C-like language. And finally, IntraJ, which is the Java compiler used during the demo, which is in turn is based upon XtendJ, which you may have heard about yesterday. Now, there are a number of hard requirements and soft recommendations to use your tool with CodeProber. Anything built with JustAdd fulfills both the hard and nice-to-haves requirements at the same time. So if you're interested in building something for CodeProber, try out JustAdd maybe. It's a meta compiler, which our group works a lot with. CodeProber is also actually being used for education right now. So there was an instance of a compiler course earlier this year where students used it to debug their C compilers or C-like compilers. And there's currently ongoing a course in program analysis where the labs are heavily centered around CodeProber. So it's an essential part of the course. This is one area where we're lacking a little bit. We haven't done a really good evaluation of what students think. We just informally ask them, hey, what do you think? And overall, the response is, oh, it's pretty good. This we will do better in the future, or this is something we want to improve in the future. But students seem to be happy. Now, you may think that, okay, that was cute. In the demo, I showed a very small file, but it does actually work for larger files as well. So we do some benchmarking in the paper, and I'm just going to focus on this dot in the top right here. This simulates a scenario where the user has 15 probes on screen, so 15 of these small windows. This is quite cluttered, but it is doable. There's over 900 files totaling 96,000 lines of code on the source path. And there's some jar files on the class path as well. I don't remember how many. And the user edits a single character inside CodeProber, and we can reevaluate all probes in just under 40 milliseconds. And it scales roughly linearly, so if you have a project with 1 million lines of code, you should expect like half a second of response time, perhaps a little more. Now, this is only possible thanks to a few things with our tool. Well, first of all, we look at extremely simple sub-analysis. We don't want to measure the time. We want to measure the overhead of using CodeProber. We don't want to measure the time of doing a complicated analysis that takes 10 minutes to run, because then the y-axis would be 10 minutes here as well. So very simple analysis. Also, our tool does on-demand evaluation, which is crucial to getting good performance. And it does incremental parsing on a file level. So even though there's 900 files on the source path, it only ever reparses one file. All right. Oh, I'm ahead of time. Where did I forget to talk about something? Yeah, so... So finally, one tricky technical issue with implementing this was, okay, the user has created a probe, then they changed the source document. How do we keep track of where they created the probe? Because they're moving it around. Like if I'm... let's go back to this variable declarator is final. Like if I'm moving this like up and down, that's fine. That works relatively easily. What if I move it like this inside of an if statement? Now the AST is structurally very different, but still it's able to track the declarator. And to do this, we came up with something we call node locators. So it's a little background and terminology. This to right, I've illustrated a very small AST. The root node is a statement node, and then the node we're looking for, or we're trying to locate, is this var decal at the bottom. Now, one way you can describe the position of this var decal is just to describe its link to from the root. So saying from the statement, go to the block, then go to the list, then go to the var decal. A little bit like navigation instructions in Google Maps. And if you write down all these steps, that can be used to locate a node. So that's what we mean with node locator. The problem is, what step types do you use? So in most ASTs, or all that I know of, there's some sort of parent-child relationship, but there are other step types available as well. And there are step types you can synthesize on top of the tree that aren't actually in the underlying native AST. So what types do you use? In which order do you combine them in order to maximize for speed and accuracy? Because any given node can be described by an infinite number of node locators in theory. Sorry. So we came up with 3 step types: child, function, and tull. So child is just the parent-child relationship I mentioned earlier. It has one parameter, which is the index, and it says something like, go to the 4th child node. Function is just a function invocation, so very sort of general, but it's necessary to access rewritten parts of the tree, or parts of the tree that aren't visible from the beginning. So if you do desugaring or optimization or dynamically loading classes, this is necessary. Finally, type at location doesn't exist natively in any trees that I know of, but this is something CodeProbber manages from the outside. And this describes a position by, or describes a node by original line and column, as well as an AST node type. Something like go to call expression at line 5, column 12. All of these have upsides and downsides. A child step is very simple, it's very fast, but it adheres very strictly to the structure of the AST. So in the example I showed where I wrapped something in an if statement, if I used child steps exclusively, it would break, because I'm now further into the AST than I was before. Function steps are fantastic. They're very versatile. You can do everything, but it's hard to create. We cannot, on a general level, implement this. We need help from the underlying tool, which we want to avoid as much as possible. Tull is very resilient. Imagine we're locating something at line 5, as it says here, and the user adds a new line at the beginning of the file. Then we just change the 5 to a 6, and we don't need to understand this grammar or how this language is being parsed. We just assume that if you had a new line at the beginning of the document, then the target node will exist further down as well. I think that's always true, but I don't know for sure. Problem with tull is that sometimes it can be slow. In the example I showed in the benchmark, where you have 100,000 lines of code on the source path, if you apply a tull from the root, then it needs to search through all 900 files, which is very slow. And it can also be ambiguous. There can be multiple nodes that match your criteria. So CodeProbber creates these locators for you. You never have to do it yourself, but it might be interesting to just see what do they look like using the syntax from the previous slide. So there's basically 3 different categories of nodes, or mainly 3. The first one is real nodes, visible nodes that the user actually typed. For example, this integer literal here. Normally, this is located with 2 steps. And steps are, the way you apply them is you start at the root, you apply the first step, then you use that as your origin for applying the second step, and you go on, and so on, until the end of the locator list. First, we begin with a child 0, which means go to the first file. And I mentioned earlier, applying tull at the root of a multi-file AST is very slow. So this goes to the first file, which happens to be the file representing CodeProbber, and then apply a tull step within that file, which is unambiguous and fast. You can also interact with nodes that don't really exist, or that are derived from your analyzer. For example, I showed you the rendering of the control flow graph. You can actually interact with both the entry and exit node. And the way you would reference this entry node, which exists somewhere vaguely here, is to first find the method declaration, so this entire F, and then arbitrary function invocation entry here. So I mentioned this is how we access parts of the tree that are created while the analysis is running. And finally, you can also interact with built-in types. For example, in Java, if you want to define the class, the declaration for Java lang string, well, yeah, we can interact with it in this way. On the root node, there's a function called getLibCompletionUnit. Again, CodeProbber manages to find this automatically for Justad. Like I said, we need help from the underlying tool in how to identify function steps. And we currently implement it for Justad, so this won't work great for everyone, but in Justad, you'll find that there's a function called getLibCompletionUnit with an argument, Java lang string, and then we find a tull there with the type class declaration. Note that the start and end is 0, 0. This is expected for built-in code, or built-in code that doesn't originate from a normal source file, but it's completely fine, it works. All right, to summarize, our contributions in the paper are threefold. The idea of property probes is a way of interacting with your program analysis tool. It doesn't replace unit tests. It doesn't replace normal breakpoint step debuggers. It's just another tool in the toolbox that's sometimes nice to rely on. CodeProber is our implementation or realization of this idea, which we use, like I said, we use in some courses now, and people seem happy. And node locators was a technical requirement to implement CodeProber, but it's not actually bound to property probes. You can use it in other areas as well. So if you don't want to build something that tracks an AST node, you can just rip out node locators as is. So with that, there's 2 links on screen. On the left one is the source code to CodeProber. The right one is a CodeProber playground where you can try it out in your browser. You don't need to download a single thing. We just run it inside of CodeSpaces, which is free for a certain number of hours each month. In case you're curious, you don't want to download and set it up on your machine. With that, thank you for listening.
Questions, please.
Oh, yeah. Oh, I'm sorry. I'm holding on to this.
Hi there. So I noticed that you had a lot of probes when you were doing your demo there. At least it looked that way. So how long does it take to write a probe? How much effort is it to write a probe to support a particular analysis?
How long does it take to write a probe? So, okay, so one of the requirements to explore things, the way we implemented CodeProber today, is the functionality must be available as a method on the AST node itself. And CodeProber just iterates through all methods with reflection. So really, if you implemented it as a method, it should just pop up automatically. Again, if you implement it with just add, there's 2 lines of code you need to add in your main function, and it should just work. So yeah, anything you already implemented should be explorable here. It depends. Also, yeah.
So it would be nice if you could do some control experiments to see probably students if they can find a bug or correct a bug more efficiently with property probes or with the classic debugger. So they have some ideas.
We have talked about this. Yes, we have talked about this, and it would be very interesting to investigate. I don't know how. There's very few people who are in the target audience where this. I don't know how, but yes, we have talked about this, and something we want to do in the future. I just don't know how to design the experiment yet.
We can talk a little bit about that. So can you tell me one example where property probes will be useful, but the same job cannot be done with the classic debuggers? Do you have some examples?
So one downside with JustAdd is that you write your specification in what's called a JRAG file, and it generates a lot of Java files, and the Java files are what runs. But the Java files don't look very much like your original specification, and your debugger will only run in the derived code. So it's really hard to run a debugger when you use JustAdd. That's part of the reason why we wanted to do this. So in general, any meta compiler that sort of generates files from your specification, I think this could be a nice alternative because debuggers can be hard to use in those cases.
But in the case of Java, you have a SMAP with this kind of thing. You have the expansion. Okay. Thank you. In the case of Java, just in the, I don't know if there is something like that. When you have something generated and you are working, you have 2 levels of debugging. You have a tool that is named SMAP distributed with Java that permits to connect something in the generated part with the original part, so that you can deal debugging. So why don't you use that instead of this kind of tool?
As far as I know, that doesn't exist for JustAdd, so that's why we don't use it. But in cases where it exists, sure, a normal debugger can be used. But I think creating a probe and playing around with it is very convenient. It's very quick, whereas starting a debugging session, seeing, oh, it behaves like this, changing the code a little bit, restarting the debugging session, it's much slower. We're saying much as in a few seconds slower, but it adds up. This is, of course, personal preference, but I think it's just nice overall. Yeah.
Yeah.
Thanks for the talk. When I'm using a debugger, I'm using, what do you call them again? The watch expressions. I sometimes abuse the watch expressions to actually have them do a side effect and influence the state of the program
Wow.
during debugging, just to get to easily get to a certain point where I want to be, for example. Can you imagine writing property probes that do some sort of side effects? Do you imagine that might be useful?
So in general, we recommend that you use on-demand evaluation and no side effects in the tree, because we want to do some caching, and we want it if you inspect a small analysis like this is final. Well, that's a bad example. If you inspect something, it should behave the same no matter if a larger probe has run before or after or not at all. Like, yes, side effects make the value of probes much worse. So in general, this is not something we want to support or not something we recommend. But you can have side effects in the tree, you just shouldn't. We don't stop you.
Thanks.
Okay, the last question. Okay.
Well, thank you for your talk again. Perhaps we should do a more modest proposal than side effects, and that's just allowing like arbitrary expressions instead of only having a single property values. Have you thought of that?
Arbitrary. So you would.
Well, arbitrary side effect-free expressions.
What would those expressions look like?
Well, yeah, is final is a bad example, but for example, you want to check if a particular instruction is created, so you check the assembly and do a filter on a particular opcode or something.
Okay, that's something I think we have discussed, where we want some sort of query language within CodeProber. You can say, select all integer literals with the value 5, for example, as a starting point to, because that's sort of what you described, I think. So as a starting point to start your exploration journey.
Yeah, in this particular example, but why would you restrict it to only a particular query language and not just arbitrary expressions over properties?
I'm sorry, I don't understand. How would such a query language look like?
Well, just like when you have regular watch expressions, you can put any Java in there,
Yes.
and it will, well, give you a result that you can inspect in the thing. Why not have that in property probes?
It's an interesting question. I don't know. Again, sorry. Yeah, no, I don't know how it would look in this tool. It's something we can talk about. Yeah. Yeah.
You want to ask a question? No. The last question.
Regarding the last point about like query language, there's prior work on incremental parsing in tree sitter, which might be interesting to incorporate here, because there's a query language in which you can do the type of query you want and gives exact source spans, and it can integrate with the other analyzers that you've shown, right?
Yes, we have. Wait, I'll go back. So tree sitter is within the domain of parsing, and that's something we intentionally isolated ourselves from because it's an implement. Yeah, it's strongly connected to the language you're working with, and we want to stay language independent. But yes, there could be some special cases, like if you're using tree sitter, we can explore queries on top of that tree. Yeah, that could be a way to do it. Yeah, thank you.
Okay, thank you for an interesting talk. Let's thank the speaker.